Welcome to the deep dive. Today we're really digging into something crucial, maybe often skipped over, but, well, fundamental for data science and machine learning success. We're talking about the real importance of data shape.
Right, it's like the blueprint for your data set.
Exactly, the initial blueprint. And if you get that wrong, you're building on, pretty shaky ground. And here's something stark. Solid data validation, getting that shape right. It's not just like good hygiene, it can seriously boost predictive accuracy. We're talking up to 30%.
That's significant. And think about the flip side, too.
Yeah, what's really fascinating, maybe a bit shocking, is that apparently up to 85% of errors in AI development, they trace right back to poorly curated inputs.
85%. Wow. It really is that garbage in, garbage out principle, isn't it? Like trying to build a skyscraper on sand, as you said.
Totally. So, okay, knowing it's crucial is one thing, but how do we actually start to read that blueprint? What are the first signals? Like mean, median, mode. What do they tell us?
Okay, so mean, median, mode.
Yeah.
We're kind of our first look at the data center. But honestly, for what we're talking about, the real story is often in how they differ.
How they differ, okay.
Yeah. That's your standard average, right? But it's super sensitive to extreme values, outliers.
Right, like the classic example of income data. A few billionaires walk in.
Exactly. And suddenly the average is meaningless for most people. That's where the median shines. It's just the middle value when you line everything up. So it stands firm against those outliers. Gives you a much truer picture for skewed stuff, like income.
Okay, so median's more robust for skewed data. What about mode?
Mode's simpler, just the most frequent value. Really invaluable when you're looking at categorical data, like most popular product color or something.
Got it.
But here's where it gets really interesting. By seeing how these three measures relate, just comparing them, you can immediately get clues about the data shape. Things like skewness, is it lopsided? Kurtosis, how pointy or flat is the peak? Or even multimodality does it have, like multiple humps?
And how do you see that visually?
Histograms are key. Box plots, too. They make these shapes really jump out at you. And recognizing what I call shape outliers, not just extreme points, but unusual patterns in the distribution, that takes a bit more experience.
That's a great distinction. So it's not just about single weird numbers, but weird shapes. And if we miss this, we could draw totally wrong conclusions.
Absolutely.
So tying this back, how does understanding these shapes actually impact building, effective machine learning model?
Oh, it's huge. It impacts model performance right across the board. Take parametric models like your standard linear regression.
Okay.
They're very sensitive to their assumptions. One big one is normally distributed errors. And if we connect this to the bigger picture, if you plot the residuals, the errors, and you see this kind of wave-like pattern, that's a dead giveaway. The model's specified wrong. The linearity assumption is broken.
Right, so the shape of the errors tells you if the model's even appropriate.
Precisely. Then you have distance-based models. Think KANN, SVMs.
Okay.
They fundamentally rely on calculating distances between points. So imagine you have features on wildly different scales, say house price in the millions and number of bedrooms, maybe 1 to 5.
The price number is just vastly bigger.
Exactly. So the distance calculation gets completely dominated by the house price, the number of bedrooms. Almost irrelevant noise in that calculation.
So the model becomes effectively deaf to the smaller scale features, even if they're important.
That's a great way to put it. Deaf to important signals. Even tree-based models, which are generally more robust to this stuff.
Yeah, they're usually pretty hardy.
They are, but they still benefit a lot from smart pre-processing, especially if your data is really skewed or imbalanced. Good pre-processing helps them make better splits, better decisions, leads to better performance.
Okay, so it seems like no model is truly immune. Given these challenges then, what are some actionable strategies? How do we deal with this?
Right, good question. A big one is definitely how we handle outliers. But this raises an important point. Outliers aren't always errors, right?
True. Sometimes they're the most interesting points.
Exactly. Just removing them wholesale can be dangerous. You might actually stop your model from spotting critical, rare events. Think about fraud detection, Ari. The fraudulent cases are the outliers you want to find.
Okay, so just deleting them isn't the answer.
Often no. So instead of just removing them, consider how you scale your features. A really good approach here is using robust scaler.
Robust scaler. Okay, what does that do differently?
It uses the median and the interquartile range, the IQR, which is basically the spread of the middle 50% of your data.
Okay.
Because it uses median and IQR, it's way more resistant to being pulled around by those extreme values. It's probably the most resistant scaler to outliers.
So it scales things fairly, even if you have some crazy high or low values, letting the model still hear all the signals, like we said.
Precisely. It helps mitigate the impact without just throwing away potentially valuable data points.
That makes a lot of sense. So ultimately, really understanding your data's shape isn't just like step one. It feels like it's maybe the single most important thing guiding your decisions throughout the whole process.
I absolutely believe so. For you, the learner, listening right now, the key takeaway really is this.
Yeah.
The very best machine learning models, they're built on a foundation of meticulously understood and prepared data. You have to know its shape.
Know the shape.
Yeah. And here's a little provocative thought to leave you with. Next time you get a data set, before you even think about algorithms or models, just spend some real time looking closely at its shape. What hidden patterns, what biases might you uncover just by looking?
Okay, let's unpack this. Today we're doing a deep dive that goes a layer deeper than the usual machine learning models. We're getting into the foundational engineering.
Right. Data structures and algorithms.
Exactly. The mission is to really look under the hood of that black box and see how the physical organization of data shapes everything.
And you can't start that conversation without talking about the biggest trade-off there is.
Time versus space.
Time versus space. You can't escape it. I mean, think of it like this. Imagine you have a massive library.
Okay.
If you just have a giant, unorganized pile of books, finding one specific title means you have to look at every single book.
That's your linear time, your O of n.
That's O of n. But if you invest some effort and memory, that's the space cost to build a really good index system.
Then you can find it almost instantly.
In logarithmic time, O of log n. And that trade-off, that decision between speed and memory, that drives, well, everything in data science.
So let's talk about the most fundamental building block, the array.
The array, the bedrock.
If I need pure speed, that's my go-to, right? But how does it actually get that famous O of 1, that constant time access? It feels a bit like magic.
It's pure structural engineering. Think of a long row of numbered lockers.
Yeah.
All right next to each other in memory.
Contiguous memory.
Right. And the machine doesn't have to search. It just does a simple calculation. Base address plus the index times the size of each element.
It just jumps straight there.
It jumps, an instantaneous O of 1 calculation. Doesn't matter if you have 10 lockers or 10 million.
And that mathematical jump is exactly why arrays, and of course matrices, are the backbone for libraries like NumPy.
Absolutely. It enables that parallel processing, the vectorization you need for something like, say, linear regression.
But arrays are rigid. What happens when your data is messy and dynamic, constantly changing?
Well, then you need flexibility. And for that, you turn to the linked list.
Ah, the scavenger hunt analogy.
Exactly that, yeah. Each piece of data, each node, is scattered in memory, but it holds a little pointer, a clue to the next one.
So you lose that instant O of 1 access for retrieval.
You do. But what you gain is the ability to insert or delete elements. Anywhere in that chain in O of 1 time is perfect for, data streams or buffers.
Okay, so we have speed and flexibility, but what about organizational logic? How do we build decision-making into the structure itself?
Now you're talking about trees. Hierarchical structures.
Their whole purpose is efficiency through elimination, right?
Right. Think of the game 20 questions. That's the perfect way to grasp their O of log n search performance.
You can narrow down 1 million possibilities in what, about 20 steps?
Because you slice the problem space in half with every single question.
Which is the exact principle behind decision trees.
And gradient boosted trees, all those ensemble methods. Each node is just a yes or no feature test, trying to reduce what they call impurity until you get a clear prediction.
So if trees give us logical speed, what if I need the absolute fastest retrieval possible?
Then you bypass all that hierarchy and go straight to hash tables.
We're back to O of 1 again. But it's a different mechanism than the array.
Totally different. Imagine a massive warehouse. You give the system a key, and it performs a little math trick on it, the hash function.
And that function just spits out a coordinate.
Spits out a coordinate, row 5, shelf 12. It's a near instant lookup. Indispensable for things like label encoding when you're turning categorical data into numbers.
Speaking of massive scale, we have to talk about tensors, the engine of deep learning.
A tensor really just generalizes everything we've talked about. Scalar, a vector, a matrix. They're all just simpler tensors.
So a batch of color images isn't just a matrix.
No, it's a 4 tensor. You have an index for the batch, the height, the width, and the color channel. And that structure is what makes vectorization possible.
And vectorization is really the power switch for modern hardware like GPUs.
It is. It lets PyTorch or TensorFlow update thousands of weights at the same time during backpropagation, not one by one.
Okay, last big problem. What about sparsity? The big data issue where your matrix is like 99% zeros.
You can't afford to store all that in nothing. It's a huge waste of memory.
So you need a kind of structural cheat code.
Precisely. You use a sparse format, something like CSR compressed sparse row.
And that just stores the important stuff.
It only stores the non-zero values and their coordinates. That efficiency hack is what made huge computations like Google's original PageRank even possible.
So to pull it all together, there's a real synergy here. Arrays and tensors for the raw math, trees for the decision logic, and hash tables for just super fast mapping.
And understanding that synergy is what turns you from someone just applying libraries into someone who can actually engineer a scalable model.
Here's where it gets really interesting.
So researchers are now pushing beyond these traditional sort of static structures like B-trees and hash maps. They're experimenting with something called learn data structures.
Which means?
It means they're literally using small machine learning models to replace the index itself. The model learns the distribution of the data and predicts the location of a key in memory.
So the tool for organizing the data is itself a product of machine learning.
Exactly. It suggests a future where our fundamental tools of data organization are these recursive self-optimizing systems. Pretty wild idea.
Okay, let's unpack this. You hear the word algorithms just about everywhere, right? Shaping everything from what you see online to how packages find your doorstep. But they often feel really abstract, maybe like a black box. So today, we're going to try and cut through that abstraction. We're going to deconstruct algorithms right from first principles and hopefully reveal just how profoundly they underpin our world.
Absolutely. And at its heart, really, an algorithm is, well, it's a precise set of steps, finite steps, step-by-step instructions, basically, designed to solve a very specific problem or, perform a task.
Like a recipe.
Exactly like a recipe. Think of it as the conceptual blueprint. It's the logical sequence, and it's totally abstract, language agnostic.
Yeah.
It's the pure idea behind the solution before it gets turned into code or anything runnable.
Right, the pure idea. And this blueprint thinking, it's not just for computers, is it? This precise sequential problem solving. It seems pretty fundamental to how we think, too.
Oh, completely. It has defining characteristics, right? Each step has to be unambiguous.
Right.
It needs to finish. That's the finiteness. It takes something in, an input, does something, and gives something back, an output.
And it needs to be general enough to work on different inputs, not just one specific case.
Yeah.
And effective, like actually doable.
Precisely. Think about tying your shoes. That sequence of steps, that's an algorithm. Or a navigation app, finding the best route. Algorithmic thinking is really a core human skill.
Okay, so here's where it gets really interesting for me. The relationship between that abstract algorithm, the idea, and an actual computer program. People often use those terms interchangeably.
They do, and it's a key distinction. The algorithm, again, is that abstract blueprint. The formula, totally language agnostic. A program, that's the concrete implementation. It's taking that algorithm and writing it in, say, Python or Java or C++ on.
Okay, so like the architect's drawing versus the actual house built from it.
Exactly that. The drawing has the logic, the structure. The house is the physical thing built using that logic. The program is where the algorithm lives and runs.
Got it. So how does that logic, that blueprint, actually tell the computer what to do? How does it direct the code?
Well, pretty much every algorithm, no matter how simple or complex, follows this universal pattern. Input, process, output, IPO. You give it data, that's the input.
Right.
It performs a set of instructions on that data. That's the process.
The steps.
The steps, exactly. And then it produces a result.
Simple enough. But how does it handle complexity, choices, repetition?
Well, that's where control flow comes in.
Yeah.
There are basically three fundamental structures. You've got sequential execution, just doing tasks one after another in order.
Okay.
The conditional logic, the if this, then do that, otherwise do something else. That lets it make decisions.
Makes sense.
And finally, iterative structures, loops. Repeating steps over and over, maybe until condition is met. That's incredibly powerful for processing lots of data or refining results.
And that processing power, especially with iteration, must be why algorithms are so crucial in data science, right? With the sheer amount of data we have now.
Indispensable. Absolutely critical. Algorithms automate these incredibly complex processes on massive data sets things humans just couldn't do manually, not at that scale or speed. They turn raw, messy data into actual, actionable insights. And they do it with high precision, consistency.
And they enable predictions, right?
Exactly. Predictive capabilities are huge. They let us see patterns, make forecasts. Without algorithms, big data is mostly just noise.
Can you give us some concrete examples? Where are they making a big difference in data science?
Sure. Think about predictive analytics, forecasting sales for a business, or a bank assessing credit risk for a loan. That's algorithms at work. Or personalized recommendations, when your streaming service suggests a movie you might like.
Yeah, sometimes spookily accurate.
Right. That's algorithms analyzing your past behavior. Also, customer segmentation, grouping customers for targeted marketing, and critical stuff like real-time fraud detection in financial transactions.
Okay, that connects directly to machine learning then. It feels like algorithms aren't just tools for ML. There's something more fundamental.
They are absolutely the bedrock of machine learning, no question. ML at its core is about computers learning from data, finding patterns, and making predictions or decisions without being explicitly programmed for every single scenario. Algorithms provide the structure, the framework for that learning process. They enable the pattern recognition, the optimization like getting better over time, and the ability to generalize to new data.
So machines learn in different ways using different algorithmic structures. What does that landscape look like?
Broadly, there are three main types, three paradigms. First is supervised learning. Here, the algorithm is trained on data that's already labeled. You give it examples of inputs and the corresponding correct output.
Like teaching it, this email is spam, this one isn't.
Exactly. So it's used for classification, like spam filters, or regression, like predicting house prices based on features like size and location.
Okay, supervised. What else?
Second, unsupervised learning. Here, the data is unlabeled. The algorithm has to find patterns and structures on its own. Think clustering, grouping similar items together without being told what the group should be, like finding different segments of customers based purely on their purchasing habits.
Interesting. And the third?
Reinforcement learning. This one's different again. The algorithm learns by doing, by interacting with an environment. It tries actions, gets feedback in the form of rewards or penalties, and learns strategies to maximize its rewards over time.
Ah, like how AI learns to play complex games or how self-driving cars learn to navigate.
Precisely. Autonomous systems often rely heavily on reinforcement learning.
Wow, okay, so you've got supervised, unsupervised reinforcement, and presumably many specific algorithms within each. How does anyone choose the right one?
Yeah, that raises a really important question. The truth is, there's no single best algorithm. It's not like there's one magic bullet. The choice depends heavily on the specific problem. Are you classifying something? Predicting a value? Finding groups?
Right.
It also depends on your data. How much do you have? Is it ladled? Is it messy? And what do you need from the output? Just accuracy. Or do you need to understand why the algorithm made a certain decision? Interpretability.
So it's more art than science sometimes.
There's definitely an element of craft to it, yes. Understand the strengths, the weaknesses, the assumptions of each algorithm. It's often an iterative process. Try one, see how it does, maybe try another. The art of algorithmic craftsmanship, you could say.
Okay, so pulling this all together, algorithms are these fundamental, precise sets of instructions. They're beneath almost all computational problem solving today. They really are the logical architecture of our digital world, enabling all this amazing automation and prediction we see.
That's a great way to put it. And what's fascinating here, I think, as these algorithms become more and more woven into the fabric of society, making decisions in finance, healthcare, even justice, understanding their principles, how they work, what their limits are, where potential biases might creep in, that stops being just a technical issue. It really becomes an ethical imperative, doesn't it, for everyone? We need to ensure they're used responsibly, beneficial.
That is a crucial point. Understanding the blueprint is key to shaping the house responsibly. A really profound thought to leave everyone with. Definitely keep pondering the algorithms, visible and invisible, that shape your world.
Welcome to the Deep Dive. Today, we're really getting into the foundations. We often talk about AI, machine learning, all the flashy code.
Right, the algorithms themselves.
Exactly. But underneath all that, there's this, elegant mathematical structure.
The real engine room.
Yeah. So our mission today is to unpack what we're calling the trinity of math for data science: statistics, calculus, and algebra. And crucially, why they matter, not just as theory, but practically.
And knowing this trinity, that's what lets you really innovate, I think. You move past just plugging things into libraries.
You actually understand how it works.
Precisely. How and why. That's the key to building something new, or even just properly troubleshooting what you have.
Okay, so let's start with the first one. Algebra. You called it the language of data. What does that mean in practice? Like if I have data points.
Right. So imagine your data, say, features of a house, square footage, number of bedrooms, age. Algebra gives us the tools to represent that. A single house, that's often a vector, like a list of numbers.
Okay, one list for one house.
Yeah. And then if you have, hundreds or thousands of houses in your data set, you stack those vectors up.
And that becomes...
a matrix. Rows are your houses, columns are the features. It's a really neat way to organize everything.
But it gets more interesting, right, with things like matrix multiplication. I hear that's huge in deep learning.
Oh, absolutely huge. It's not just tidy organization. It's the computational workhorse. It's how layers in a neural network talk to each other, how transformations happen.
So why is it so fast compared to, say, looping through data?
Well, that's vectorization. Your computer's processor, especially GPUs, are built for this. They use something called CMD, single instruction, multiple data. Meaning they can do the same math operation, like an addition or multiplication, on many different data points all at the same time, in parallel.
Instead of doing them one.
And by one, by one.
Exactly. Forget for loops for this kind of scale. Vectorization is dramatically faster. It's honestly what makes training massive models even possible today. Got it.
And if you want to understand how these deep networks work, you have to realize data points are never just isolated numbers. They're organized.
So they're like collections of numbers.
Exactly. They're vectors in this massive high-dimensional space. That n-dimensional reality where AI operates, it's the map of the world for the model.
And that map gets really complex, right? I mean, when we move into modern systems, things like video processing, we're not just talking about vectors anymore. We go way past matrices into these higher order tensors.
Yeah, think about a standard RGB image on a screen. You might picture it as a flat grid of pixels, a 2D matrix. But it's actually a rank 3 tensor. It's got height, it's got width, and then it has that crucial third dimension for the red, green, and blue color channels.
So without that third dimension, you'd be losing all the color information, all the context.
You'd be losing almost everything. And to handle these huge structures, you need some serious algebraic power tools. You need decomposition.
Which is just a fancy way of saying we need to break these things down.
We have to. And arguably the most powerful tool we have for this is singular value decomposition, SVD.
Hold on. I've heard SVD can be pretty computationally intense on its own.
Yeah.
So are we just shifting the problem around? What makes it worth it?
Because SVD is like AI's compression artist. It gives us a mathematical guarantee. It finds what are called singular values, which measure the energy or the really critical information in the data.
Okay, so it finds the most important bits.
The most important bits, which means we can get the absolute best low-rank approximation.
So what does that practically mean for, say, a large language model?
It means we can actually deploy it. We use SVD to compress the weight matrices of these LLMs. You can often throw out over 30% of the information and still keep almost all of its reasoning ability.
Wow, that's huge.
It's the only way to make it feasible to run.
All right, this is where it gets really fascinating for me. Okay, so algebra gives us the structure, the language. What about statistics? You framed it as the grammar of insights.
Yeah, if algebra organizes the words, statistics helps us understand the meaning, the story the data is telling. It deals with patterns, relationships, and crucially, uncertainty.
Right. I know, maybe not the most thrilling word, but honestly, it's the bedrock, the compass guiding everything in AI and machine learning.
It really is.
Our plan is simple. Take your sources on stats and ML, pull out the absolute must-knows, and basically shortcut your path to really understanding this stuff. Let's maybe think about it like we're building a customer churn model. Stats is our guide.
That's a great way to frame it. And what's really fascinating is how statistics takes all that raw, messy data and turns it into something reliable, something interpretable.
Right.
It's what makes an AI system trustworthy, not just predictive. It gives us actual confidence, say, in those churn predictions we're making.
Okay, so it's like a universal language then, for anyone working with data, whether that's healthcare, marketing, whatever.
Exactly, a common ground.
So let's unpack the main branches. I gather there are two. How do they work together?
Yeah, two main ones. And critically, they aren't really separate things. It's more like a cohesive feedback loop.
Yep.
You've got descriptive statistics first.
Okay.
That's all about summarizing the data you know. So for our churn example, think calculating the average age of customers who churned, or the variation in their contract lengths, the mean, the variance, that sort of thing.
Just describing what's there.
Precisely. Then inferential statistics comes in. It uses samples like our historical churn data to make, well, reasonable guesses or predictions about the bigger picture, the unknown population of all our customers.
Making the leap from the sample to everyone.
Exactly. And here's the loop. Say our descriptive analysis shows the churn data is really skewed, maybe lots of very new customers leaving. That insight immediately tells us, okay, be careful. We probably shouldn't use certain inferential methods that assume data is nicely balanced, normally distributed.
Right. So it guides the next step.
It guides us towards maybe transforming the data first or using different kinds of statistical tests that don't rely on that assumption. It's synergistic.
Got it. So descriptive stats really kicks off our understanding. It's the core of exploratory data analysis. EDA, right? Revealing things like central tendency mean, median, and how spread out the data is standard deviation.
Absolutely. Think of it as your first diagnostic tool. It flags potential data quality problems before they mess up our churn model.
Like finding errors or weird values.
Yeah, exactly. Things like kurtosis, which tells you if your data has fat tails, meaning lots of extreme values, or the interquartile range, the IQR, that maps the middle 50% of your data. These are great for spotting outliers because they aren't as easily fooled by those extreme values as, say, the simple mean is.
Okay, so it helps clean things up.
Definitely. And that leads to practical steps. Like if you have missing age data, maybe you fill it in with the median age, which descriptive stats help you find reliably. Or using z-score standardization that's scaling features so they all contribute fairly to the model. Or maybe a log transformation if your data is heavily skewed to make it behave better for certain algorithms.
Okay, that makes sense. So we use descriptive stats to understand and prep the data. Now, building on that, we move into inferential statistics using that feedback loop you mentioned. The goal here is generalizing, right? Making sure our churn model works on new, unseen data, not just the data we trained it on.
Precisely. Generalization is key. And often people just report a single accuracy score for their model, like 90% accurate. But inferential stats gives us better tools. Like confidence intervals. Instead of just saying 90%, maybe we find a 95% confidence interval for our churn model's accuracy is, say, 88% to 92%. That range gives a much more robust and honest picture of how reliable that model likely is in the real world.
A range of possibilities. I like that.
Yeah. And this is where it gets really powerful, I think. Inferential statistics brings in hypothesis testing. It's basically the scientific method applied to machine learning.
Okay, how does that work?
Well, you start with a default assumption, the null hypothesis, or H0, H dollars. This assumes there's no effect or no difference. For our churn model, H dollars might be customer age has no impact on churn.
The status quo, kind of.
Kinda, yeah. Then you have the alternative hypothesis, H1, H$1, which is what you're actually trying to claim customer age does impact churn.
Okay.
Then you look at your data and calculate a p-value. The p-value tells you the probability of seeing results like yours if the null hypothesis were actually true.
Okay. Probability of the data if H0 is true.
Exactly. And if that p-value is really small, usually less than a threshold called the significance level, often 0.05, it suggests your observed data is pretty unlikely under the null hypothesis. So you reject H$, in favor of H$1.
So you'd conclude age probably does impact churn.
Correct. It's super useful for formally validating which features are actually important for your model, or for A/B testing comparing two different versions of your churn model, maybe using something like a t-test to see if the performance difference is statistically significant, or if it could have just happened by random chance.
That sounds incredibly useful, but also like something you could easily misuse. Which brings us to statistical rigor and potential pitfalls. You mentioned statistical significance. Is that the same as being important in the real world?
Great question. And no, absolutely not. That's a huge pitfall. Statistical significance having a low p-value just means the observed effect is unlikely to be due to chance. It doesn't automatically mean the effect is large enough to be practically significant or meaningful in a business context. You might find a statistically significant difference that's actually tiny and irrelevant.
Okay, so don't just chase low p-values.
Definitely not. And another big one is misunderstanding the p-value itself. A p-value of 0.05 doesn't mean there's a 5% chance the null hypothesis is true. Remember, it's the probability of the data, assuming the null is true. Subtle, but important.
Right, the condition is key.
And then there's the multiple comparisons problem, or sometimes called the multiplicity mess. Basically, if you run lots and lots of statistical tests purely by chance, you're going to get some statistically significant results, even if nothing real is going on.
Like testing dozens of features for the churn model.
Exactly. Imagine testing 20 features where actually none of them truly affect churn. With that standard 0.05 significance level, you'd still have roughly a 64% chance of finding at least one feature looks significant just by random luck.
Yeah, okay. That could lead you to put useless features in your model.
Precisely. It contributes to overfitting, building a model that learns noise instead of the real signal. That's why it's crucial to also report the effect size. This tells you the magnitude or strength of the effect, not just whether it exists statistically. It gives you that practical perspective.
Okay, so p-value plus effect size gives a fuller picture. It seems clear then that descriptive and inferential statistics really work hand in hand. You need both for solid data science.
Absolutely indispensable. From that initial look at the data with descriptive stats, right through validating your final churn model with inferential methods, statistics ensures integrity.
So it keeps everything honest from start to finish.
Yeah. So what does this all mean for you listening? I think mastering these statistical foundations is what really separates someone who can just use ML tools from someone who's a true expert.
Building things that actually work reliably.
Exactly. It lets you build models that aren't just performant on paper, but are genuinely robust, reliable, and crucially interpretable. And that really shapes the entire future of trustworthy AI. So maybe consider, how does applying this level of statistical rigor change how you approach your next data project?
Makes perfect sense.
Sure.
Okay, Trinity Part 3. Calculus, the engine of learning. Why engine?
Because calculus is fundamentally about change, how things change in relation to each other. Think of your car's speedometer. It's showing the rate of change of distance over time. That's calculus.
So how does that apply to a model learning?
Well, models learn by adjusting their internal parameters to get better predictions. Calculus helps us figure out how to adjust them efficiently. We start with differentiation. For one variable, the derivative tells you the slope, the instantaneous rate of change.
Like how house price changes just with square footage.
Right. But models usually have tons of variables. That's where the gradient comes in. It's like a multi-dimensional derivative.
A compass.
A compass, yeah. It points in the direction where things are changing the fastest, usually, where the model's error is increasing most steeply. Imagine you're blindfolded on a hillside. The gradient tells you which way is straight uphill.
Okay, so if the gradient points to where the error gets worse...
You go the opposite way. And that's the core idea behind gradient descent.
The ball rolling down the hill analogy.
That's the one. You calculate the gradient of your error, take a small step in the opposite direction, recalculate, take another step, and repeat. You iteratively roll down the hill towards the point of minimum error.
And models use this constantly during training.
Constantly. A key example is backpropagation in neural networks. It uses the chain rule from calculus to efficiently calculate how much each connection in the network contributed to the final error.
So it knows exactly how to adjust everything.
In a very clever, calculus-driven way, yes. It distributes the error signal backwards through the network.
Wow. Okay, so bringing it all together quickly for our house price example.
Yeah.
Algebra structures the house data in matrices.
Yep.
Calculus, through gradient descent, finds the best settings for the model by minimizing the prediction error.
Right. It tunes the engine.
And statistics tells us how good the predictions are, measures the uncertainty, and validates the whole thing.
Exactly. They're completely interwoven. Algebra provides the language, statistics, the grammar for understanding, and calculus the engine for learning and optimization.
A really powerful combination.
It truly is. And understanding that interplay, the why behind just running the code, that's where real mastery lies. It's about building AI you can actually trust because you understand its foundations.
So, a final thought for everyone listening. If you move beyond just using the pre-built tools and really grasp this mathematical bedrock, what currently complex problem could you start to genuinely tackle? Something to think about.
Welcome to the deep dive. Ever find yourself looking at just a massive amount of data, maybe sales numbers, customer notes, sensor data, and just wondering, how do I find the key thing? How do you cut through all that noise to see what's actually going on before you even start thinking about complicated models? Well, that's what we're digging into today. exploratory data analysis, or EDA. Think of it like a decoder ring for data, a way to let the data itself tell you its secrets.
It really is. EDA isn't just another step. It's more like the fundamental way you get to grips with a data set. Understand its shape, spot the patterns, find the weird bits, the anomalies.
Yeah, the detective work.
Exactly. That's where it starts. It lays the foundation for, well, everything else.
Okay, let's unpack this a bit then. So, ED. It's like a systematic way to poke around in data sets, right? Summarize them, often using visuals.
Precisely.
Yeah.
The main goal is to figure out what the data is actually saying on its own terms. It's not about rigidly testing some hypothesis you already had.
So you let the data lead the way without sort of prejudging it.
That's the core idea. And it's got history. This approach, this sort of flexible, curious attitude, it came from John Tukey, a brilliant American mathematician back in the 70s.
Tukey, right. I've heard the name.
Yeah. He felt statistics was maybe too focused on testing hypotheses. He argued we should use data to suggest hypotheses in the first place. It really enriched the whole discovery part of analysis.
So it's more about the mindset being flexible, inquisitive.
That's a great way to put it. It's an attitude.
And here's something really interesting, Heather, again. It's not just a one-off check.
Oh, absolutely not. It's a cycle. You analyze, you visualize, maybe you transform the data a bit, then you analyze again to see what else pops out.
Like you might be looking at sales data, just exploring, and suddenly you see these clear seasonal spikes you never noticed before.
Exactly. And that one insight could send you down a totally new investigation, maybe about why those spikes happen. Deeper insight.
Right. It's like peeling an onion.
And if you connect that to the, let's say, the practical side, EDA is basically your first line of defense. Risk management strategy, really.
How so?
Well, it's absolutely critical for catching things early. Glaring errors, missing information, duplicates, those weird outliers that don't fit.
The stuff that can really mess things up later if you don't catch it.
Precisely. Without that cleanup, any models you build later might be biased, they might not work well, or worse, they could lead you to completely wrong conclusions.
The classic garbage in, garbage out problem.
You got it. EDA stops that and makes sure your foundation is solid, like checking the ground before you build a house.
Makes sense. So when people actually do EDA, I keep hearing Python is the go-to tool. Why is that? What makes it the main engine here?
Yeah, Python's huge in this space.
Yeah.
Its ease of use is a big part, but it's also the ecosystem. Libraries like pandas are fantastic for data handling.
Like getting a quick summary.
Exactly. Things like df.info to see data types and missing values, or df.describe for basic stats, instant snapshots. And then for the visual side, you've got Seaborn and Matplotlib. You can create a heat map to quickly see correlations, or a pair plot to visualize relationships between many variables at once. It's just very powerful and flexible.
So the tools make that investigative process much faster and easier.
Definitely. But beyond the tools, the real magic is how useful EDA is everywhere. I mean, across so many different industries.
Any cool examples spring to mind?
Oh, sure. Think about Walmart. They use ED constantly. Analyzing customer buying habits helps them stock shelves better, obviously. But they also use it for things like predicting delivery times more accurately, or even figuring out the best box size to use for shipping to cut down waste, all from exploring their data.
Wow, okay. That's pretty sophisticated stuff from just exploring data.
It is. Or there was a case with a fruit supplier. They kept getting complaints about overripe fruit. So they used EDA. They plotted complaint data against things like delivery routes, storage times, temperatures.
And they found a pattern.
They did. They pinpointed when and where the fruit was most likely to become overripe. This led them to change their picking, packing, and storage methods. And the result, a massive 64% drop in complaints.
64%, just from looking at the data they already had?
Just from exploring it properly, it shows how powerful simply looking can be.
It really does. So it sounds like being good at EDA isn't just a bonus for data scientists, it's table stakes, right?
Foundational.
Absolutely fundamental. It directly impacts your ability to make good data-driven decisions and really unlock what's inside any data set. So wrapping this up then, what's the big takeaway for you listening? EDA basically takes that raw, maybe messy data and turns it into something you truly understand, a resource. And that understanding lets you build better models, find smarter solutions, all because you listen to the data first.
Which leads to maybe a final thought to chew on. Think about the data you encounter. What patterns, what stories might be hiding there, just waiting for someone curious enough to look. That ability, Tukey talked about understanding data before jumping to conclusions. It's just as crucial now as it was back then, maybe even more so. All right, welcome back to the deep dive. Today we have a pretty ambitious goal.
We do, a big one.
We are going to try and demystify machine learning. I've got this stack of notes, and honestly, half of it looks like hieroglyphics.
It always does.
The mission today is to strip away what the experts call the cargo cult of jargon.
It's not as scary as it looks, I promise. We're going to try using the Feynman technique.
Okay, I like that.
Yeah, if we can't explain one of these algorithms to, say, a smart 12-year-old, then we don't really get it ourselves.
Perfect. So, big picture. For the longest time, coding was just rules. If this happens, then do that.
Explicit instructions.
But the sources all describe this huge shift to something called inductive pattern recognition.
Right. So instead of you writing the rules, you just give the computer a pile of data vectors, matrices, and the answer key. And you just tell it, you figure out the rules.
And it finds things we would miss.
It finds relationships a human would never, ever spot.
Okay, let's start simple then. Yeah, supervised learning, it's a huge part of machine learning. It's all about using labeled data where we already know the right answer to train a model. The model learns to map inputs to outputs. But, and this is crucial, it all hinges on the data. Garbage in, garbage out, as they say. Data quality is absolutely paramount.
Okay, right. So garbage in, garbage out. Let's unpack these models. If we're starting simple, where do we begin? Linear regression, maybe? That's the one where you're basically trying to draw the best fitting straight line through your data points on a graph, like pulling a string taut across them, minimizing those distances.
Exactly, yeah. The least squares method, technically.
Yeah.
Linear regression is, well, it's beautifully simple, very interpretable. We call it a white box model because you can see exactly how it's making predictions. Think about predicting salary based on years of experience. You can literally see the weight it gives to experience. Its strength is that clarity.
But it has limits, right? It assumes things are, well, linear.
Precisely. It assumes a straight line relationship, and the real world is often much messier than that. It doesn't always fit a neat line.
Okay, so if linear regression handles continuous stuff like salary, what about predicting categories like yes or no, spam or not spam? That's logistic regression, isn't it?
That's right. And what's fascinating here is how it does classification. It takes a linear model's output, sometimes called log odds, but then squishes it. It uses this function, the sigmoid function, that looks like an S shape. It forces the output into a probability, a value between 0 and 1.
Ah, okay. So not just yes or no, but maybe 95% chance this is spam, or a specific risk percentage for a disease.
Exactly. That probabilistic output is incredibly valuable for making nuanced decisions. Much more info than a simple binary yes-no.
Makes sense. Now, what if the relationships in the data aren't straight lines or simple S-curves? What if it's really complex nonlinear stuff? Decision trees come in here, yeah. They seem more like flowcharts, asking a series of if this, then that questions to split the data.
Yep, that's the core idea. It recursively partitions the data, asking questions at each step like, is feature X greater than value Y? Trying to create groups or leaves that are as pure as possible, meaning ideally each final group contains data points of only one class. We measure that purity or lack thereof using things like Jani impurity, trying to minimize the mix-up.
And the big plus is you can follow the path, right? See the logic.
Totally. Very interpretable. But, here comes the downside. They were notoriously prone to overfitting.
Overfitting? That's like memorizing the training examples, including all the random noise, instead of learning the actual underlying pattern.
You got it. Like a student who memorizes answers but doesn't understand the concepts. It performs great on data it's seen, but falls apart on new, unseen data. Doesn't generalize well.
That sounds like a big problem. So how do we stop these models from just memorizing everything? How do we, discipline them?
That's where regularization comes into play. This is really interesting stuff. Regularization basically adds a penalty to the model based on its complexity, usually related to the size of its coefficients or weights.
A penalty for being too complex?
Sort of, yeah. Two common types are lasso, or L1, and ridge, or L2. Think of it geometrically. Lasso uses a penalty that often forces some coefficients to become exactly 0.
0. So it kicks features out.
Exactly. It performs feature selection, which is super useful. Ridge, on the other hand, uses a penalty that shrinks all coefficients towards 0, but rarely makes them exactly 0. It's good for handling situations where your input features are highly correlated.
Okay, so ways to keep models in check. What about combining models? I hear about ensemble techniques, the idea that lots of simple models together can be better than one complex one, the wisdom of crowds.
That's a perfect way to put it. Ensemble methods combine multiple weak learners to create a single strong learner. And there are two main flavors. First, There's bagging. Think of random forest. It builds multiple decision trees independently on different subsets of the data and then averages their predictions or takes a majority vote. It works in parallel, reducing the model's variance, making it less sensitive to the specific training data.
Okay, parallel processing. What's the other flavor?
That's boosting. This is sequential. Imagine a student working with a tutor. The first model tries to solve the problem, gets some things wrong. The next model focuses specifically on the mistakes the previous one made. Each subsequent model pays more attention to the errors, step by step, trying to reduce the overall bias. Gradient boosting is a key example here.
And isn't there one called XGBoost that always seems to pop up?
Yes. XGBoost is essentially a supercharged, highly optimized version of gradient boosting. It's got built-in regularization, handles missing data well, and is computationally very efficient. That's why it often dominates data science competitions. It's very powerful.
Got it. Okay, one more I wanted to ask about. Naive Bayes. The name naive sounds not great. Why naive?
Yeah, it does sound a bit suspect. It's based on Bayes' theorem, which is solid probability theory, but it makes a very strong naive assumption that all the input features are independent of each other given the class.
Independent. But features in the real world are often related, aren't they? How can it work if it assumes something that's usually wrong?
That's the counterintuitive part. It turns out that even though that independence assumption is almost always technically false, the algorithm often works surprisingly well in practice. Especially for things like text classification, spam filters are a classic example. Its simplicity makes it incredibly fast and efficient computationally. You just need to handle potential issues like the zero frequency problem. What happens if you see a word in testing you never saw in training? But there are simple fixes for that.
Wow. Okay, so we've covered quite a range, from simple lines to complex ensembles and even naive approaches. When you're faced with a problem, how do you choose? It sounds like there's no single best algorithm.
Absolutely not. There's no silver bullet. It's always a trade-off. You have models like linear regression, logistic regression, decision trees, even naive Bayes. They tend to be more interpretable. You can peek inside and understand why they're making certain predictions. Then you have models like random forests and XGBoost, which often give you higher predictive accuracy, sometimes significantly so, but they can be more like black boxes. Harder to understand the internal logic.
So it depends on the job, interpretability versus accuracy.
Exactly. What does your data look like? What are your project's priorities? Do you need to explain the why behind predictions, maybe for regulatory reasons? Or is pure predictive power the main goal? That balance dictates your choice.
What a fascinating journey, really. From finding the best line to combining weak learners into something powerful. It's this constant balance, isn't it? Simplicity versus complexity.
It really is. And maybe here's something for you, the listener, to chew on. That complexity we often chase for better predictions. It frequently comes at the expense of being able to clearly understand why a decision is being made. So it really pushes us to think critically. How much transparency are we willing to sacrifice for performance? In machine learning, and maybe in other decisions too.
That's a great point. How much transparency versus performance? Definitely something to think about in how we all process information and tackle problems. Think of us as your shortcut to, well, really getting informed. Today, we're jumping into unsupervised learning algorithms. These are like data detectives finding hidden patterns, but without any predefined answers. Our goal. Break these complex ideas down, Feynman technique style, so you really get what makes them tick.
That's a great way to put it. You know, I often think of Sir Isaac Newton and the apple. He didn't get data labeled gravity. He just observed, asked questions, and inferred the laws himself. That's unsupervised learning in a nutshell. It's discovery, finding structure before you even know exactly what prediction you want to make.
That really frames it well.
Yeah.
So, okay, how do we start finding these patterns? Clustering seems like a big one, right? Grouping similar things together.
Absolutely. And K-means is probably the most famous. Think center of the crowd. It finds the center, pulls points towards it, recalculates the center with this little two-step dance. You see it everywhere. Customer segmentation, even image compression, grouping similar colors.
K-means sounds pretty efficient then, but what are the catches? Like you have to tell it how many groups, and do they need to be, I don't know, certain shapes?
Yeah, exactly. It's fast, but you do need to specify K, the number of clusters up front. And it definitely prefers clusters that are kind of spherical and roughly the same size. If your data looks different, maybe long and thin clusters or different sizes, K-means might struggle a bit.
Okay, so if K-means has those limits, what's next? You mentioned DBS scan before, something about density?
Right, DBS scan. It takes a totally different approach. Instead of centers, it looks for dense regions. It uses two parameters, epsilon, that's like a search radius around a point, and minpeats, the minimum number of neighbors needed to be considered core. This lets it find clusters that aren't just round, they can be any shape. And crucially, it can identify points that are all alone as noise.
Noise, so like outliers, things that don't fit.
Exactly, which makes it fantastic for anomaly detection. Think finding weird credit card transactions, that sort of thing.
And you don't need to tell it K beforehand. That sounds really useful.
No K needed, which is a big plus. The trade-off. Tuning epsilon and min ports can be, well, a bit tricky sometimes. Especially if you have lots and lots of dimensions, density gets weird.
Right, high dimensions. We should come back to that. But first, there's another clustering type, hierarchical.
Ah, yes, hierarchical clustering. Think of building a family tree, but for your data points. It starts with every point as its own tiny cluster, then merges the closest ones step by step. You get this visual called a dendrogram, the tree diagram.
Okay, like a branching structure showing who merged with whom.
Precisely. And different linkage methods decide what closest means when you merge clusters. Like Ward's method tries to keep the merged clusters nice and evenly sized, so it's good for things like biological taxonomy or, again, market segmentation maybe.
And the cool thing with the dendrogram is you can kind of decide later how many clusters you want just by looking at the tree.
That's a huge advantage. You run it once, get the tree, then decide where to cut it to get your clusters. But the downside is it can get computationally heavy. For really massive data sets, tracking all those potential merges takes time. It starts with every point as its own tiny cluster, then merges the closest ones step by step. You get this visual called a dendrogram, the tree diagram.
Okay, like a branching structure showing who merged with whom.
Precisely. And different linkage methods decide what closest means when you merge clusters. Like Ward's method tries to keep the merged clusters nice and evenly sized, so it's good for things like biological taxonomy or, again, market segmentation maybe.
And the cool thing with the dendrogram is you can kind of decide later how many clusters you want just by looking at the tree.
That's a huge advantage. You run it once, get the tree, then decide where to cut it to get your clusters. But the downside is it can get computationally heavy. For really massive data sets, tracking all those potential merges takes time.
Okay, so that covers finding groups. But what if the data itself is just too much? Too many features, too complex to even start?
That's a perfect lead-in to dimensionality reduction. We need ways to simplify. And the classic here is principal component analysis, PCA. Its goal is to find new axes, principal components that capture the most variance, the most information in your data. Imagine squashing your data onto a line or a plane while losing the least amount of spread.
So it simplifies things, makes it easier to maybe visualize or process, like for image compression again.
Exactly. Visualization, compression, and it's a key weapon against the curse of dimensionality.
Okay, PCA sounds powerful for simplifying. But interpreting those new principal components, are they easy to explain? Like, what do they mean?
That's the rub. They're mathematically efficient, capturing variance, but they're abstract combinations of your original features. So telling a business user what principal component 1 means can be tricky. It shows separation, but maybe not the why in simple terms. And just quickly, while we're here, it's worth mentioning LDA, linear discriminant analysis. It also reduces dimensions, but it's actually supervised.
Ah, right. So LDA needs labels. How does its goal differ from PCA then, if both reduce dimensions?
Totally different goal. PCA just looks for the directions of maximum variance in the data, regardless of labels. It's exploratory. LDA, because it has the labels, specifically tries to find the dimensions that best separate those known classes. Think improving a classification model, like for credit risk, where you know who defaulted and who didn't. PCA explores, LDA separates known groups.
Got it. PCA for exploring structure, LDA for enhancing classification. Okay, let's shift to some maybe foundational ideas that pop up across these methods.
Sure, like K nearest neighbors, KNN, usually taught as supervised, right? Find the KN closest labeled points and vote.
Yeah, for classification or regression, but unsupervised.
Well, the core idea of finding neighbors is super useful without labels too. For anomaly detection, if a point's average distance to its K neighbors is really high, maybe it's an outlier, right? It's far from everyone. Or even filling in missing data, look at the values of the nearest neighbors and estimate.
So the basic mechanism of finding neighbors can be used in creative, unsupervised ways. That's neat.
It really highlights understanding the core idea. And speaking of neighbors and distances, that brings us to the curse of dimensionality you mentioned.
Right. The curse. What actually is that? Sounds ominous.
It is, a bit. Basically, as you add more and more dimensions or features, the space your data lives in gets incredibly vast and empty, really sparse. counterintuitively, everything starts to seem far away from everything else. The concept of a close neighbor starts to break down.
So distance-based algorithms like KNN or even clustering, they just stop working well.
Pretty much. The distance has become less meaningful, which is why dimensionality reduction like PCA isn't just nice to have. Sometimes it's almost essential to make these algorithms work effectively in high dimensions.
Makes sense. And underlying all these distances, how we measure closeness itself matters, right? The metrics.
Absolutely fundamental. Euclidean distance is your straight line, as the crow flies. Good baseline, but sensitive to outliers. Assumes things are kind of Gaussian. Manhattan distance is like city blocks, only horizontal and vertical moves. Less sensitive to outliers, maybe better if data seems more Laplacian. And then cosine similarity just cares about the angle between data points, not the magnitude. Great for text data, where word counts might vary wildly, but the topic, the direction, is similar.
Wow, so choosing the metric isn't trivial. It's a core assumption about the data.
It really is. It shapes what similar means.
Okay, so with all these methods, k-means, DBS scan, PCA, how do you tune them? In supervised learning, you have the right answers to check against. Here, you don't. So how do you know if it's good?
That is the million-dollar question in unsupervised learning. There's no single right answer or objective score like accuracy. It comes down to a mix of things. Heuristics, like looking for stable clusters. Domain knowledge. Does this grouping make sense in the real world? And ultimately, human judgment. Can you, the analyst or the user, derive useful insights or value from the patterns it reveals? The data scientist becomes more of a facilitator for discovery.
So we've really dived deep into this world of unsupervised learning. It's clearly more than just algorithms. It's a whole mindset about exploration and discovery in data.
Exactly. That lack of ground truth isn't just a challenge, it's the whole point, in a way. It's the opportunity. It lets us find structures, signals, connections in huge amounts of unlabeled data that we might never have even thought to look for. Truly hidden insights.
So maybe the final thought for you listening is, knowing these hidden structures exist, how might that change the kinds of questions you even think to ask about the world around you? Something to ponder.
Ever wondered how intelligent systems learn complex tasks? I mean, not from perfect instructions, but purely by experiencing their world.
Right.
Today, we're plunging into reinforcement learning, RL. It's this really fascinating area of machine learning. It's all about how agents learn to make sequential decisions, basically through trial and error.
Exactly. And our mission for you in this deep dive is, well, to cut through the noise, unpack the core mechanics of RL, and clarify why it's such a game changer for problems demanding optimal decisions over time. You should get some real aha moments about how these systems learn from often quite delayed feedback.
Okay, let's unpack that. Our sources really stress that reinforcement learning is, at its heart, concerned with an agent making a sequence of decisions.
Yeah, in an environment that's dynamic, maybe uncertain.
Right, and the goal is always maximizing some kind of cumulative reward signal.
And what makes RL so potent, I think, is that unlike systems you train on static pre-labeled data sets.
Like in supervised learning.
Precisely. RL actively discovers the best behavior through continuous interaction, trial and error. It's really uniquely suited for that sequential decision-making where the impact of an action isn't always immediately obvious.
Let's try and ground this. The classic analogy is training a dog, right? Dog's the agent, the living room is the environment. Actions like sit, get a reward, maybe a treat. But, for our deep dive, let's maybe pivot instantly to something more complex.
Yeah.
Think about an autonomous drone navigating a forest.
Okay, yeah.
Here, the state isn't just dogs sitting by the door. It's like this high-dimensional input of LiDAR data, GPS, camera feeds, much more complex.
That interactive loop, though, that defines RL, you always have these 5 core components.
Yeah.
The agent that's the decision maker.
Got it.
The environment, the external world it interacts with. The state that's its current perception of the world, like that drone's sensor data.
Right.
The action, what the agent chooses to do. And the reward, which is that immediate numerical feedback, good or bad.
Okay, so those are the building blocks. Agent, environment, state, action, reward. But how does it actually decide what action to take in a given state? That gets us to the policy, right?
Exactly. The policy is essentially the agent's master strategy. Think of it as a map from states to actions.
A map, okay.
And policies can be deterministic, like always do this action in this state. Or they can be stochastic.
Stochastic. So probabilistic.
Yeah, providing a probability distribution over actions. Deterministic is fine if the world is perfectly predictable.
But it rarely is.
Right. So stochastic policies are vital. They help with exploration, trying new things, and they're crucial in, say, adversarial settings like poker. If you're too predictable, you get exploited.
Okay, that makes sense. You need some randomness.
A bit, yeah, to learn robustly.
So building on that policy idea,
Yeah.
if a reward is like a single paycheck you get right now, then the value function sounds like it's more about the long game, like a financial forecast for the next decade, the total expected reward down the line.
That's a great way to put it. It's this forward-looking perspective. It's often formalized by something called the Bellman equation, which is, well, it's really the backbone of many RL algorithms.
Why is it so central?
Because it lets us break down this huge, complex, long-term optimization problem into smaller, recursive steps. It essentially says the best value of being in a state now is the immediate reward you get, plus the discounted best value of whatever state you end up in next.
Discounted, meaning future rewards are worth a bit less than immediate ones.
Exactly. It encourages prioritizing achieving goals sooner rather than later, and it also keeps the math as manageable. It helps the agent weigh long-term gains against short-term ones.
So as the agent is learning, refining its policy, figuring out these values, it hits this classic problem, right? The exploration-exploitation dilemma.
Ah, yes. The ultimate dilemma, isn't it? It's like finding a restaurant you absolutely love.
Yeah.
Do you just keep going back, exploiting that knowledge? Or do you explore that new place across town that might be even better, but could also be terrible?
Right. The risk versus the known reward.
Precisely. That balancing act. Exploiting what you know works versus exploring new possibilities for potentially much bigger payoffs. Getting that balance right is absolutely core to learning optimally in RL. Too much of either isn't good.
Okay, that provides a really good picture of the mechanics inside RL. But, stepping back, we already have supervised learning, unsupervised learning. What is it fundamentally that makes RL stand out? What problems can it solve that the others can't really touch?
The key differentiator, I'd say, is the credit assignment problem.
Credit assignment. Explain that.
Okay. In supervised learning, the feedback is instant. You show it a cat picture, it says dog, you immediately say, no, that's a cat. The feedback is right there, tied to that specific input.
Got it. Direct link.
But in RL, imagine playing chess. You make a brilliant move on turn 10, but you might not actually win the game until turn 50. The profound challenge is figuring out which of the many actions you took before that win were actually responsible for it. Was it that move on turn 10, or something on turn 35, or a combination? Assigning credit back in time to the right actions. That's tough.
Because the reward is so delayed.
Exactly. And this is precisely why techniques like Q-learning and temporal difference learning, or TD learning, are so fundamental in RL. They give us elegant ways to propagate that delayed reward signal back through the sequence of states and actions, even if we don't have a perfect model of how the environment works.
Well, it's like learning a really complex skill.
Sequential delayed feedback and the algorithms designed to handle it, that's what truly makes RL unique.
And we see this playing out spectacularly in video games, right? They become this amazing sandbox for RL.
Oh, absolutely. I mean, from classic Atari games like Miss Pac-Man's Simple Actions, but millions of possible game states all the way up to DeepMind's AlphaGo Mastering Go.
Which has an astronomical number of states.
Astronomical. And OpenAI's Dota 2 AI. These RL agents learn strategies that are often at or even beyond human level. They frequently use deep neural networks now to handle the sheer complexity, approximating those policy and value functions by basically playing millions and millions of simulated games.
You mentioned something earlier about intentional imperfection in commercial games. That sounds counterintuitive. Isn't RL all about finding the optimal strategy? Does needing imperfection mean RL has limits? Or is it something else?
That's a really sharp question. It's less about a limitation in RL's ability to find the mathematically optimal path, and more a challenge in defining what optimal means when humans are involved. An AI that finds some obscure loophole to win every single time might be optimal according to its reward function, but it would be incredibly boring or frustrating for a human player.
Right, ruins the fun.
Exactly. So it's more an adaptation. Game designers carefully shape the reward signals, or sometimes they combine the learned RL behaviors with more predictable scripted actions. The goal shifts from pure mathematical optimality to creating an opponent that's engaging, challenging, maybe even feels fair, even if it's not technically playing perfectly. It reflects that the goal is often more nuanced than just winning.
That makes a lot of sense. So wrapping up then, reinforcement learning gives us this distinct Really powerful way for agents to learn the best policies just through interacting with their world.
And brilliantly balancing that need to explore new things with exploiting what already works, all to maximize that cumulative reward over the long haul.
And it's clever ways of tackling that credit assignment problem, handling delayed rewards, and adapting on the fly.
Yeah, it means the applications are just exploding well beyond games. We're seeing it increasingly in robotics, personalized medicine, complex financial modeling, sophisticated recommendation systems. It's really versatile.
We have covered a lot today. So, next time you see an AI making what looks like smart sequential decisions, maybe pause and consider that intricate dance. It's doing actions, states, rewards, exploration, exploitation, constantly learning.
It really is a fascinating process.
And maybe think about this. How might understanding this exploitation balance change how you approach learning new skills, or even making important decisions in your own life? Something to chew on.
Today, we're jumping into deep learning, or DL, which is, the engine behind pretty much every major AI breakthrough we see.
From your phone's camera to the huge language models.
Exactly. So our mission today is to get past the buzzwords and really figure out why this specific type of AI became so incredibly powerful.
And it's interesting because at its core, deep learning is really defined by its architecture. It's just multiple layers of computation, kind of inspired by the brain.
Inspired by the brain, right?
But the real game changer isn't the structure, it's what it can do. It can take in huge, messy piles of unstructured data images, text, sound, and just figure out the patterns for itself.
So it's this idea of depth then. How does just adding more and more layers actually change what the model can learn?
It enables something called hierarchical feature learning. You can think of it like a pyramid. The first few layers learn really basic stuff.
Like edges and colors in a picture.
Exactly. Simple edges, textures, that sort of thing. But then the deeper layers start combining those little pieces into much more complex concepts. Like it'll put edges together to see the curve of a wheel or the shape of an eye.
I see. So it builds understanding.
It builds understanding layer by layer. And the data on this is just undeniable. We saw a 152-layer network outperform an 18-layer one on the ImageNet challenge by almost 10 percentage points?
That's a huge difference. But if the core math, this thing called backpropagation, was figured out way back in the 1970s, were we just waiting around for better computers? Did we miss the boat for 30 years?
That's the million-dollar question, isn't it? And the failure wasn't really algorithmic. I mean, the math was solid. It was a resource bottleneck.
A resource bottleneck.
Yeah, they had this beautiful mathematical engine, but they had absolutely none of the fuel. They didn't have the massive data sets or the raw compute power. It was like having a Ferrari engine, but only bicycle fuel to run it on.
Okay, so the fuel had to arrive, and that was the ImageNet project, right?
That was the catalyst. Between 2009 and 2012, Fei-Fei Lai's team saw this exact problem, this data deficit, and they built ImageNet. We're talking 12 million labeled images.
A massive undertaking.
And that set the stage for what we call the AlexNet moment in 2012. They used GPUs, graphics cards, to just power through that data. And it didn't just improve the result, it slashed the error rate. It proved that scaling up data and compute wasn't just helpful, it was everything.
So they had the fuel and the engine. What was next?
Well, even with the power, the process was still a bit inefficient. It needed a better lubricant, you could say. And that innovation was the rectified linear unit, or ReLU.
ReLU.
Sounds technical. But the idea is simple. It's just a more efficient on-off switch for the artificial neurons. It stopped the deep networks from seizing up during training, which is what made training a 152-layer network even possible.
Okay, that makes sense for images. But what about something messy, like a conversation or just a long piece of text? I've heard about this vanishing gradient problem.
Right. With sequential data, older networks, they had terrible short-term memory. A signal from the beginning of a paragraph would just fade away or vanish by the end.
So it would forget the context.
Completely. And that's what led to things like LSTMs and GRUs. They have these spiralized little mechanisms, like a forget gate, that let the network very deliberately decide what old information is important to keep. That finally cracked the long-term memory problem.
And that whole line of thinking led us to where we are now with the transformer architecture from 2017. What was the big leap there?
It completely threw out sequential processing.
Yeah.
Instead of reading word by word, the transformer uses something called the self-attention mechanism to look at every word at the same time. It's massively parallel.
And self-attention is the core of every big language model today. So what is it in simple terms?
The best analogy is that for every single word, it runs a quick search across the entire sentence to see how relevant every other word is. It uses these things called query, key, and value vectors to weigh connections.
So it creates a global context.
An enforced global context instantly. It knows how the first word relates to the last word, all at once. That's its superpower.
So if you put it all together, deep learning's success wasn't one thing.
No, it's a perfect storm. It's a symbiotic relationship between, the mathematical insights from decades ago, the explosion of big data, and the sheer power of modern hardware like GPUs.
So here's the final thought to leave you with. While these DL models give us incredible performance in everything from medicine to self-driving cars, their complexity often turns them into complete black boxes. We know they work, but we don't always know why.
That's the trade-off.
And that's the critical challenge facing everyone in this field. We're constantly choosing performance over interpretability and figuring out how to balance those two things. Well, that's the next great deep dive.